Okay, so in this video, I just want to pick up on a couple of final points about the yttrium oxide Rietveld refinement. And the main things are what you should do at the end of the refinement in terms of checking things and archiving your results. The take-home message, or the most important thing in this video, is on the screen here. And it's all about the use of CIF files, crystallographic information files, for storing the information at the end of a Rietveld refinement. And I have to admit, I've never been a big fan of CIF files. I've not used them very much because there's never been any convenient software for interrogating the content of powder diffraction CIF files, and it's been very difficult to write good quality CIF files from Topaz. Unfortunately, all that's changed in the last few months. There's been a beautiful publication by Matthew Rolls from Australia on creating CIF files from Topaz, and also a new piece of software called PD CIF plotter, which you can use to interrogate the results of those CIF files. I really think that Matthew's work here is going to change the way that the powder diffraction community use CIF files, and it'll certainly change the way that the Topaz community use them. So I want to go through how to use PD CIF plotter in this tutorial. Okay, so let's start by going to the desktop, and let's just pick up with the file that we finished with at the end of previous tutorials. And that's this file here. So let me open this Rietveld refinement file in JEdit. And let's just remind ourselves where we were at the end of the Rietveld refinement. So I'll send this file to Topaz. I'll do a Rietveld refinement of the file. And I think we had an R factor of about 14.2% or something at the end of the last tutorial. Here we go, an R factor of 14.1%. So this was our final Rietveld fit. What should we do when we've finished the Rietveld refinement? What should we be checking? Well, in the last tutorial, we went through a few things. We went through checking what the R factor is. We went through checking what the goodness of fit value is. We also said that one useful thing you could do in Topaz is look at the correlation matrix. And so at the end of the refinement, it's always useful checking your correlation matrix to see if there are any large correlations in there. So any 100% correlations aren't on the main body diagonal of the correlation matrix, you should maybe start worrying about. But in this case, everything looks fine. There's one other thing that we didn't encounter in the previous video because the refinement was set up in a sensible way. And that thing is limits on parameters. So you might remember that in the previous tutorial, we wrote a little equation describing the 2 theta offset of the instrument. And we put parameters on the values allowed for the 2 theta offset. So lots of the parameters you refine in Topaz have got limits set on them to make the mathematics more stable and to stop those parameters diverging to silly values. And one thing you have to be worried about is if the minimum and maximum values aren't set appropriately. So just for the sake of argument, let me say that I set my minimum value to be minus 0.04 degrees and my maximum value to be plus 0.04 degrees. The refined value of the 0 point is actually outside that range. So if I do the refinement again in Topaz, my R factor is a little bit higher. It's now 15.268%. And if we go back to the input file, very conveniently, Topaz has put a little warning on this line, giving us a warning in red that that parameter has hit its limit. Now, during a Rietveld refinement, if any parameter has hit its limit, you need to be suspicious, firstly about that parameter, but also about all the other parameters in your model that might be affected. So you really need to make sure that parameters are within their specified limit. So if I set that back to plus or minus 0.05, well, let's set it to where it was before, plus or minus 1 degrees, and do the refinement again. Everything should be sensible. One place where you find this comes up quite a lot is in temperature factors. So you know that the atomic displacement parameters, or the temperature factor that we refine in Topaz, should never be a negative number. It doesn't make any physical sense for a temperature factor to refine to a negative number. So often I find that people put a limit on the temperature factors. They put a limit of 0, a low limit of 0, so that that quantity can never go negative. My personal view is that if a quantity wants to go negative in a Rietveld refinement, you should allow it to go negative. So that temperature factor would go to a negative number. And then what you need to be thinking to yourself is, why is that temperature factor negative? Why is it refined to an unphysical quantity? It's probably that some other aspect of your model, probably in this case the absorption, is incorrect. So you should always be very careful about min-max values, and certainly check at the end of your refinement that there are none of those flags in your input file. Okay, let's come on to archiving the results of the refinement. One of the things that you might want to do is write one of these crystallographic information files for saving the results of your refinement. Now, Topaz has always had built into it a basic way of creating a CIF file. Let me delete the line that's there and start from scratch. So in Topaz, the type of CIF file it's always been able to write out is a structural CIF file. So if we go to the X insert menus and we go to Topaz version 7 menus, and we go to the phase level structure, and we go to the output menu, there's a command in here called generate CIF output. If I double click on that command, it adds the line to my input file, and we can write out a file called basic.cif. Okay, so if I do the refinement again, I get a file written. At the end of the refinement, it says file basic.cif has been written to. Okay, so now in my directory, I've got a file called basic.cif. If I open it up, that really is just a structural CIF. So it's got the refined cell coordinates, it's got the space group, and it's got the fractional atomic coordinates. So that might be enough for what you're doing. If all you want to do is visualize the structure, I tend to use a program like Vesta for looking at my structures in more detail. That file is certainly of a quality that it can be read by Vesta and you can look at your structural model. But if you're trying to archive the results of your Rietveld refinement properly, then what you need to be doing is not just writing out the structural part of the CIF, you ought to be archiving the experimental data and the calculated model and some details about how you did the refinement. And that's where Matthew's routines and PD CIF plotter are particularly useful. So what Matthew has generated for us is a series of macros that we can use to write CIF files from Topaz. If you haven't got them already, if you do Google search for something like Topaz, Wiki, CIF, and see what we come up with. The first link there is a link to a page that Matthew has created on the Wiki, which tells you how to download his CIF macros, and it tells you how to run this program called PDF CIF plotter. And there are also links to the publication in Journal of Applied Crystallography on the paper, or some information on the IUCR Powder Commission page about the project. So have a look at those pages about how to install things. Essentially, the way that you have to install things is Matthew's CIF routines are a series of macros. And we mentioned in an earlier tutorial that Topaz has got a file associated with it, which sits in the main Topaz directory called topaz.inc. And we looked at that in an earlier tutorial. And it defines some of the built-in macros that Alan has created for Topaz. What you can also set up is a file called local.inc. And so I've got a file called local.inc, which also gets read by Topaz. And that's got all my personal macros, ones that I've written myself. But I've also got a line at the top of my local.inc called include pdf.inc and include cif.inc. So all of the macros for creating CIF files are in a file called cif.inc. So that file has to sit inside your Topaz directory. If you go to the wiki, you can download the relevant file, and I've got it sitting in my Topaz directory as a file called cif.inc. So I can open that in JEdit and just have a look at it. It's a whole series of macros that do everything we need to do to create a CIF file. So once it's set up, you'll never need to look at this file again, but you can just use it when you do a Rietveld refinement. So if we go back to our input file here, there are a couple of extra commands that we need to add to our input file to get it to write one of these CIF files. In the XDD section, all of these details are on the wiki, by the way. It's useful to give each diffraction data set its own local ID parameter. It's useful to give some extra information which will get written to the CIF file. For example, in this case, that this was a step scan powder diffraction measurement. And then in the STRA section, it's useful to set a parameter called the local CIF phase ID. So if you've got multiple structures in your fit, or even multiple diffraction patterns, you need to set these parameters so that each part of the CIF file is unique. As I say, all of the details on this on the wiki or in Matthew's paper. And then at the end of the input file, we just need a line here which is out PD CIF, and that will call the macros, it will call Matthew's macros, and it will actually write us a file called Y2O3 demo.cif. If I now send that to Topaz and I do the refinement, this time at the end of the refinement, I've got things right. The file Y2O3 demo.cif has been written. So now if I go into my folder, I should have that file available. Here it is, Y2O3 demo.cif. If you open that file up and look through it, it's got all the crystallographic information we looked at before, but it's got things like the distances and angles in it. It's got things like the experimental data, all stored in that CIF file. Just like the previous one, you can view the structural part of it in something like Vesta. So if I drag that across to Vesta, again, I can see the structure, so that's easy to view. But the beautiful thing that Matthew has done is he's created us a little plotting routine, a Python-based plotting routine, which lets us visualize the results of the Rietveld refinement as well. So to run that, there's either a Windows standalone version of it, or it's if you've got Python installed, there's a little Python module that you can put on your computer. So if I run a command line from that folder, I have Python set up here. So all I need to do is I need to type Python -m, then the name of the module, which is PD CIF plotter, and that should launch Matthew's program. If you're a Python person, you'll see that it's based on the matplotlib library, so it's very, very easy to adjust it if you want to. You get this nice little window pop up on your screen. All you need to do is load a file. A little dialog box should pop up, and I can load this Y2O3 demo.cif. And what you see on the screen once the CIF file is opened, you can see that all of the results of the Rietveld refinement are stored in that CIF file. There's a little magnifier window so you can zoom in and you can look at the quality of the fit. You can do things like show the HKL tick marks, and those have got nice little labels associated with them, so you can see what each HKL reflection is. So I've zoomed out here, and you can do things like plot the cumulative chi-squared, how the contributions to chi-squared vary across the diffraction patterns. It's a really nice way of working. You can do things like plot the data in d-spacing instead of 2 theta, if that's useful for you. It's really good even for simple Rietveld refinements. Where I find it comes into its own is if you've got a more complex analysis. And so, for example, I'm going to load a file in now, which was a time of flight neutron diffraction analysis, where I was fitting 6 banks of data simultaneously during my model. So in this particular case, there were 6 banks of diffraction data, and they've all been read in. If I click on these little buttons in the top right of the screen, here's my bank 1 fit, here's my bank 2, my bank 3, my bank 4, my bank 5, and my bank 6. So I can view all of those things. There's another window here called stack, and if I go into the stack window, I can look at all of the diffraction data in an offset way. So that can be a really useful way of looking at the data. What I find particularly useful is this surface plot feature. In the surface plot feature, what's happened here is all of the diffraction patterns, the different banks have been read in. So this is bank 1 of my diffraction data, bank 2, bank 3, bank 4, bank 5, and bank 6, all shown on a time of flight scale. But you can put those data onto a d-spacing scale, and now all of the diffraction peaks line up. And so in the low resolution bank, we have these broad peaks which don't go to very low d-spacing values, and the high resolution bank up here, we can see the much sharper peaks but over a narrower d-spacing range. You can do things like show the HKL ticks on top of that pattern, so you can see the individual reflections and where they appear in the different banks, the time of flight instrument. And you can even do things like, there's some nice little buttons here on the right, show RWP. In this particular refinement, you can see what my R factor was for the bank 6 data, bank 5, bank 4, bank 3, bank 2, and the poorly fitting bank 1 data. There's a lot of beautiful things you can do with PD CIF plotter. Of course, it's got all the functionality built into it that comes with matplotlib. Matthew's given us a nice little window here for fonts. If you want to change your font size from 16 point to 20 point for publication, you can do all of that kind of thing. Things like the goodness of fit have been written at the top of this file. The R factor, 2.75%, has been written at the top of the file. So PD CIF plotter is a great way of visualizing powder diffraction CIF files. So the combination of being able to write good CIF files from Topaz and being able to visualize the diffraction pattern part of them within PD CIF plotter, I think is a really, really useful tool. So thanks to Matthew for providing that tool, and hopefully people are going to take it on and start using it in their work. So hopefully that video has been useful. Thanks again for watching.